Welcome to this deep dive, and I think this one's really going to resonate with you, philosopher, because we're going deep, deep down to the very bedrock of math. Like where do numbers even come from? What is order? What about functions?
Those are big questions.
Huge. And to unpack this, we're going to look at the work of Ernst Zermelo. He was like obsessed with this idea of sets being this fundamental basis of, well, everything mathematical.
Yeah, this is like catnip for philosophers, right? This whole quest for absolute rigor, trying to build a whole system of math from just a few basic truths. It's wild.
Total head trip. Okay, so imagine you're a mathematician back in the early 1900s. Set theory is this shiny new tool. Seems like it can describe anything. But there's this underlying assumption called the comprehension principle. Basically, if you can define something logically, bam, there's a set for that.
Right. It's seductive, isn't it? This neat link between our thoughts, our logic, and boom, mathematical objects just pop into existence.
But there's a snag, and that snag has a name, Russell's paradox. So think about the set of all sets that are not members of themselves. Can you even wrap your head around that?
It's classic.
Total mind bender. Now, if this set contains itself, well, it shouldn't, right?
Yeah.
Because it's defined as the set of sets that don't contain themselves. But if it doesn't contain itself, then it actually fits the description, so it should be a member. Ancient, implode.
Yeah, it's a total logical knot. And it showed mathematicians that our intuitive ideas about sets were, a little too naive. The whole system was built on shaky ground.
And into this chaos steps Ernst Zermelo, our hero of the day. He was like, okay, hold on, we need to fix this. He knew that the comprehension principle was the culprit, and he had to find a better way. Enter his 1908 paper, Untersuchung über die Grundlagen der Mengenlehre SIA. It's basically ground zero for modern set theory, the first time anyone tried to axiomatize the whole thing.
Big moment. Zermelo is basically saying, let's ditch this free-for-all with sets and build a system with strict rules. Like, think of Euclid and his axioms for geometry. Same vibe.
Right. So in this deep dive, we're going to break down these axioms. We'll also look at the folks who influenced him, like David Hilbert, the axiomatic method king, and Georg Cantor, the infinity whisperer, with his whole well-ordering thing. Then we'll get into the drama, the pushback Zermelo got and how other mathematicians stepped in and made the system even better. So, philosopher, ready for a foundational adventure?
Let's do it.
First up, back to Zermelo's 1908 paper. He starts by saying, and I'm quoting here, set theory is that branch of mathematics whose task is to investigate mathematically the fundamental notions number, order, and function, and to develop thereby the logical foundations of all of arithmetic and analysis. Thus, it constitutes an indispensable component of the science of mathematics. Like, wow, right, this is big picture stuff.
He's not messing around. Zermelo's saying set theory isn't just some niche thing. It's the foundation, the core, the root of pretty much all math. If you want to understand numbers, functions, order, you got to understand sets.
And he knew the elephant in the room, that pesky comprehension principle. He was very aware that it needed restrictions. He said, and again I'm quoting, "In solving the problem this presents, we must, on the one hand, restrict these principles sufficiently to exclude all contradictions, and on the other, take them sufficiently wide to retain all that is valuable in this theory." Like, he's walking this tightrope, Keep the power of set theory, but make sure it doesn't explode.
A delicate balance. And this tension between expressiveness and consistency runs through the whole history of set theory.
Totally. So how do you actually do it? He starts with this idea of a domain, a collection of objects. And this includes sets, obviously. The key relationship here is set membership, denoted by the symbol swime.
This domain idea is crucial. It gives us a universe to work in, a place where sets can exist and interact through that membership relation.
All right, on to the axioms. First up, axiom of extensionality. It's pretty intuitive, right? Two sets are the same if they have the exact same elements. Doesn't matter how you describe them, just what's inside counts.
Yep. Extension over intension. The composition of the set, not the description, is what matters.
Next, the axiom of elementary sets. This is about the basics. The empty set, nada, zip, 0 elements. Then singleton sets, just one lonely element. And unordered pairs, 2 elements hanging out. Building blocks, basically.
The bare minimum you need to start building the set theoretic world.
Now we get to the big one, the one that's all about damage control after Russell's paradox. The axiom of separation, or Sonderungsaxiom. It says you can carve out a subset from an existing set based on a specific definite property. And here's the key difference from the old comprehension principle. You got to start with a set that's already there. No conjuring sets out of thin air based on just any old logical description. We're talking about subsets, pieces of something that already exists. That's how you avoid those nasty paradoxes.
Separation is all about controlled construction. You can't just create a set based on any arbitrary description. You have to work within the bounds of what you already have. It's like sculpting a statue. You start with a block of marble. You don't just magic it into existence.
Okay, so power set axiom. This one says that for any set, you can create another set containing all its possible subsets, like a set of all the different combinations of things inside the original set.
Power sets are all about potential. It's like taking a set and saying, let's see all the different ways we can group these elements together, and then boom, you have a new set that captures all those possibilities.
Then there's the union axiom. Imagine you have a set of sets, like a box full of smaller boxes. The union of all those sets is basically just dumping all the content of all those smaller boxes into one big box.
It's like flattening the hierarchy. You take a collection of sets and you combine them all into one giant set that contains all the elements from each of those original sets.
Now, for the one that's always a hot topic, the axiom of choice. It says, if you have a bunch of sets that don't share any elements, you can create a new set by picking exactly one element from each of those sets. Sounds simple, right?
Yeah, it's deceptively simple. And it's been the subject of intense debate, especially when you're talking about infinite collections of sets. The idea of making infinitely many choices simultaneously, even without a specific rule for how to make those choices, can get a little mind-bending.
Lastly, we have the axiom of infinity. It just says, hey, there exists at least one infinitely large set. Zermelo was like, we need this, and he wasn't afraid to just assume it. No trying to prove infinity from other principles, just straight up, it's out there.
It's a bold move, but it's essential for dealing with the vast world of infinite numbers that Cantor had revealed. If you want to talk about transfinite cardinals, ordinals, and all that jazz, you need a starting point, and that's what the axiom of infinity provides.
So to sum up, we've got extensionality, elementary sets, separation, power set, union, choice, and infinity. Quite a crew. You mentioned that some are particularly important. Like infinity and power set get us to those uncountable sets, choice is a whole other story, and separation is the workhorse. Could you unpack that a bit more?
Sure. The axiom of infinity is our starting point for infinity. Think of it like the set of natural numbers. Now, apply the power set axiom to that, and you get a set that's even bigger, uncountably so.
Right.
Do it again, and you get an even bigger set, and so on. It creates this whole hierarchy of infinities. The axiom of choice, well, we'll get into that later, but it's crucial for proving some really important things, like that every set can be well ordered. And as you said, separation is the one we use all the time. It's how we create new sets by picking out specific elements from existing sets based on some property.
Okay, so Zermelo's got this new system that's axiomatic, it's strict, it's all about control. Did it actually work? Did it fix the paradox problem, specifically Russell's paradox?
It did, and in a really clever way. Remember how Russell's paradox hinges on this set of all sets that don't contain themselves? Well, Zermelo shows that within his system, no such set can exist. It's like he used the paradox itself to show why his system was safe. Here's how it goes. Take any set M. Now, using separation, define a subset M containing all the elements of M that don't contain themselves. It turns out, and this is where the magic happens, M cannot be an element of M. If it were, we'd be right back in paradox land. So, boom, no set of all sets that don't contain themselves. Russell's paradox neutralized.
Awesome. So what about the other paradox, the one with the set that contains absolutely everything?
Right, the universal set. Well, Zermelo's like, look, without the comprehension principle running wild, there's no reason to believe this universal set even exists. You can't just gather everything up into one giant set. Separation only lets you create subsets of what's already there. You're always working within boundaries. Zermelo sums it up nicely. Not all objects X of the domain, lo, can be elements of one and the same set. That is, the domain U is not itself a set. And this disposes of the Russell antinomy so far as we are concerned. So, problem solved, again, thanks to the restrictions on set formation.
But did Zermelo actually prove that his whole system was consistent? Like, mathematically, no contradictions.
Well, that's where things get a little tricky. He knew that just because he hadn't found any paradoxes, it didn't mean they weren't lurking somewhere. He admitted that a full consistency proof was still an open question. In his own words, I have not yet even been able to prove rigorously that my axioms are consistent, but I hope to have done at least some useful spade work hereby for subsequent investigations in such deeper problems.
So he laid the groundwork, but the ultimate guarantee of consistency was still out there. Now, let's shift gears a bit and talk about the people who influenced Zermelo. First up, the axiomatic method master, David Hilbert. What was his deal? And how did it all connect to set theory?
Hilbert was all about rigor and formalization. He was like, look, if we want math to be solid, we need to start with clear, unambiguous axioms and build everything up from there using pure logic. No hand-waving, no intuition, just cold, hard deduction. And this was a radical departure from how math had been done before. Traditionally, it was all about constructing objects, like building them step by step. Hilbert was like, nope, let's define the rules first, then see what we can create within those rules.
Interesting. So Hilbert was less about the how and more about the what, the relationships defined by those initial axioms.
Exactly. He wanted to get to the logical core of math. He believed that a mature mathematical theory should be presented as an axiomatic system, like Euclid did with geometry. Define your basic terms, lay down the axioms, and then let logic take over.
So what were the core principles of Hilbert's axiomatic method?
There are a few key ingredients. First, you need a domain, a collection of objects that your theory is going to talk about. Then you need a finite list of axioms that lay down the law, so to speak, about how those objects behave. These axioms have to be like the ground truth, the starting point. Then you need proofs. And those proofs can only use the axioms and the rules of logic. No sneaky shortcuts. The goal is completeness, meaning that every true statement within the theory should be provable from the axioms. And finally, and this is a big one, consistency. Your axioms can't contradict each other. If they do, the whole thing falls apart.
So for Hilbert, if you could prove a system was consistent, then the math it described was, legit. It existed in a real way.
Yeah, he was pretty hardcore about that. Consistency was the litmus test for mathematical existence. If your system was free from contradictions, then the objects it described were considered to be real in a mathematical sense, of course. He famously said that mathematical objects are defined through axioms brought into life.
That's a pretty powerful statement. So how did all this connect to Zermelo and his set theory?
The influence is pretty clear. Zermelo's whole approach screams Hilbert. He starts with a domain, right? Then he lays out his axioms, a finite set of rules for how sets work, and he's very aware of the need for a consistency proof, even though he admits he hasn't got one yet.
And Hilbert was also really into proof analysis, right? Like figuring out what follows from what, logically speaking. How did that play into Zermelo's work?
Right. Hilbert was all about understanding the logical connections within math. And Zermelo's work on the well-ordering theorem and the axiom of choice is a perfect example of this kind of analysis. He shows that you need the axiom of choice to prove the well-ordering theorem, and vice versa. It's all about teasing out the logical dependencies.
Okay, so we've got Hilbert and his axiomatic influence. Now let's talk about the other big name, Georg Cantor. He was the infinity guy, right?
Yes. Cantor was a total revolutionary. He basically blew open the door to the infinite, showing that there are different sizes of infinity, that it's not just this one big, undifferentiated thing. And his concept of well-ordering was central to his theory.
Well-ordering. Now, for our philosopher listeners, can you remind us what that's all about?
Sure. Imagine you have a set of objects. A total ordering just means you can put those objects in a line, so to speak, where any two objects are comparable. One comes before the other. But a well-ordering is stronger. It means every subset of your set has a least element, a first element, according to your order. So the natural numbers, 1, 2, 3, and so on, with their usual order, they're well-ordered. But the integers, all the whole numbers, including negatives, they're not well-ordered because, the set of all negative integers has no first element. It just keeps going down and down.
So Cantor thought this well-ordering thing was, super important, even for infinite sets.
Totally. He believed that to really understand infinite sets, to compare their sizes in a meaningful way, you needed to be able to well-order them. He even thought it was a fundamental law of thought, something that was just inherently true about how we understand the world.
And this led him to develop his famous Aleph sequence, right? The hierarchy of infinite sizes.
Yep. The Aleph sequence is Cantor's attempt to catalog all the different sizes of infinity. You've got Aleph null, Aleph 1, Aleph 2, and so on, each one bigger than the last. And the famous continuum hypothesis is all about where the size of the real numbers, the continuum, fits in this sequence.
So Cantor's whole framework rested on this idea that every set could be well-ordered.
Pretty much. If not, the Aleph sequence might not be able to capture all the different sizes of infinity out there. And this whole idea of comparing sets based on their size, called cardinal comparability, it kind of falls apart without well-ordering.
But did Cantor ever manage to actually prove that every set could be well-ordered?
He tried, but his proofs weren't exactly rigorous by modern standards. They relied on some intuitive ideas like repeatedly picking arbitrary elements, which, as Zermelo pointed out later, wasn't a well-defined process. Zermelo was like, look, you can't just say pick an element infinitely many times. You need a rule, a system. And Cantor's attempt to show that every set has an Aleph number as its cardinality also relied on some vague intuitions and these arbitrary choices. Zermelo wasn't impressed.
So even though Cantor was a visionary, his proofs weren't quite up to snuff. And this whole well-ordering question became such a big deal that Hilbert even put it on his famous list of unsolved problems, right?
Yeah, in 1900, Hilbert presented a list of 23 problems that he thought were the most important challenges facing mathematics in the new century. And the first problem was all about the continuum hypothesis, which is basically asking, what's the size of the continuum? And this, of course, is intimately tied to the question of whether the continuum can be well-ordered. Even Bertrand Russell, the paradox guy, had his doubts about whether every set could be well-ordered.
So we've got these foundational questions swirling around, the paradoxes, the nature of infinity, the well-ordering problem. Enter Zermelo, stage right, with his 1904 proof of the well-ordering theorem. And this is where things really start to heat up.
It was a bombshell. Zermelo basically said, I can prove that any set can be well-ordered. But the catch was he needed this new principle, the axiom of choice. And this was a very controversial move.
Axiom of choice. What's so controversial about that?
It basically says that if you have a collection of non-empty sets, even infinitely many, you can create a new set by picking exactly one element from each set. Sounds pretty straightforward, right? But the problem is, it doesn't tell you how to make those choices, especially when you're dealing with infinite sets. It's like saying, there's a way to pick a representative from every country in the world, even though we have no specific rule for how to choose them. And this really rubs some mathematicians the wrong way. They were like, hold on, you can't just assume you can do that without telling us how.
So the 1904 proof sparked a lot of debate.
It was an understatement. Mathematicians were up in arms. Some questioned the validity of the choice principle, some worried about paradoxes lurking in Zermelo's proof, and some just didn't like the way he was handling infinite sets. Zermelo was like, whoa, hold your horses. And in 1908, he came back with a revised proof and, more importantly, his axiomatization of set theory. He was trying to address the criticism, make things more rigorous and clear.
So can you give us a quick rundown of that 1904 proof, just to see where the controversy came from?
The core of the proof is this idea of a choice function. Imagine a function that takes any non-empty subset of your set and spits out one element from that subset. Zermelo's like, let's assume we have such a function, call it Go. Then he uses Gogurt to define special subsets of your original set called Go sets. These are well-ordered, and their order is tied to in a very specific way. He shows that Go sets exist, that any two Go sets are like nested pieces of each other, and then he takes the union of all possible Go sets. This union, called Lo, is also a Go set, and it turns out to be equal to your original set. So your original set is well-ordered. Bam.
But that whole thing hinges on the existence of this magical choice function, right? That's where people got tripped up.
Yep, the choice function is the sticking point. It feels like cheating, like pulling a rabbit out of a hat. You're assuming you can make infinitely many choices without any rule or guidance. And that didn't sit well with a lot of mathematicians.
But Zermelo saw the importance of the well-ordering theorem, especially for Cantor's theory of infinity, right?
Absolutely. If every set can be well-ordered, then you can assign a unique cardinal number, a left number, to every set. It strengthens the whole idea of comparing sets based on their size, cardinal comparability. It was a huge step forward for Cantor's vision.
All right, so back to the objections. Let's unpack those a bit more. You mentioned three main categories.
Right. The objections were basically about the axiom of choice itself, Zermelo's overall way of handling sets, and his use of something called impredicative definitions.
Okay, let's start with choice. What were the arguments against it?
People like Emile Borel were bothered by the non-constructive nature of choice. You're asserting that a choice function exists, but you're not giving any recipe, any algorithm, any way to actually find it. It's like saying a treasure exists without giving a map. And that led to well-orderings that were, like, theoretical, not something you could explicitly describe. Hadamard made a distinction between assuming the existence of things that are fully described and things that are just, like, asserted to exist without any concrete definition. Zermelo's response was basically, look, if I want to prove cool stuff like the well-ordering theorem, I need this axiom, deal with it. He even listed problems that he thought were unsolvable without choice, showing how powerful it was. Peano also objected, saying that choice wasn't provable in his logical system. Zermelo's like, well, axioms are supposed to capture what we already do in math, and we use choice-like principles all the time.
So Zermelo's argument was more about the practical consequences of accepting choice. It was a useful tool, even if it wasn't, philosophically pure.
Yeah, he was focused on the power and utility of the axiom. It got the job done, and that's what mattered to him. He was less interested in the philosophical fine points and more interested in building a system that could handle the complexities of infinity.
What about the second objection, the one about how Zermelo was manipulating sets?
So people like Bernstein, Jourdain, and Schoenflies were a bit worried about Zermelo playing fast and loose with infinite sets, especially infinite well-orderings. They were afraid he might stumble into some hidden paradoxes, like the Burali-Forty paradox, which comes from trying to create a set of all ordinals. They thought Zermelo wasn't being careful enough, that he needed to be more explicit about the rules of the game. Zermelo brushed them off, saying that his principles avoided the Burali-Forty paradox. But to be fair to the critics, Zermelo's 1904 paper was a bit vague on the details of set formation. He was still working things out. He later addressed this more formally with the axiom of separation in his 1908 axiomatization.
All right, on to the last objection, impredicative definitions. Now, I remember this from my logic class, but for our listeners who haven't had that pleasure, what is an impredicative definition?
Basically, it's a definition that refers to a whole collection of things, and that collection includes the very thing you're trying to define. It's a bit circular, right? A bit like if defining tall as taller than the average person. The average height depends on all the heights, including the one you're trying to define. Russell and Poincaré thought these kinds of definitions were dangerous, that they could lead to contradictions. Zermelo, however, was on Team Hilbert. He believed that definitions were just about picking out things that already exist. The existence of an object doesn't depend on our ability to define it predicatively. It's all about the consistency of the system as a whole. He pointed out that impredicative definitions are used all the time in math, like defining the least upper bound of a set. And later, guys like Ramsey and Gödel showed that impredicative definitions aren't inherently bad as long as your system is consistent.
Okay, so lots of pushback on that 1904 proof. And Zermelo, being a Zermelo, doesn't back down. He comes back in 1908 with a new proof. How is this one different?
In the second proof, he switched tactics. Instead of building a well-ordering from the ground up, he sort of worked backward, starting with the set he wanted to well-order and then carefully removing elements to create a chain of subsets. This chain itself exhibited the well-ordering. He was trying to avoid appealing to arbitrary well-orderings or ordinals in the way that had bothered people before. He also emphasized the role of the subset relation in establishing the order. He was basically constructing a remainder set directly without relying on a pre-existing well-ordering.
And the axiom of choice itself got a makeover.
Yeah, in the 1908 paper, Zermelo presented a slightly different version of choice, focusing on sets instead of functions. He basically said that if you can split a set into a bunch of non-empty disjoint subsets, then there's a way to pick one element from each of those subsets and create a new set. Interestingly, later on, Zermelo kind of backpedaled on the whole choice terminology. He felt like it was misleading, that it implied some kind of conscious act of choosing, which wasn't really what he had in mind.
And we were the specific axioms that he relied on for this second proof.
He explicitly mentioned separation, power set, and his set version of choice. He also used the existence of elementary sets, like the empty set and singletons, but that was more implicit. And in his full 1908 axiomatization, he added extensionality and infinity just to make things official.
Okay, so Zermelo's system was a huge step forward, but it wasn't perfect, right? There were still some kinks to work out. Let's talk about the issues with the separation axiom even after he formalized it.
The main problem with separation wasn't the idea itself, it was the vagueness surrounding this concept of a definite property. You're allowed to separate out subsets based on properties, but what exactly counts as a definite property? That was a bit fuzzy. And paradoxes like the Richard paradox showed that you can't just use any old description you can think of. You need some kind of constraint.
So even though Zermelo defined definite property, it wasn't clear enough for everyone.
Yeah, his definition was a bit hand-wavy. He said a definite property is one whose truth is determined solely by set membership, equality, and the laws of logic. But what are the laws of logic exactly? How do you get from those basic building blocks to a complex property? Frankel was like, this is too vague, we need more precision. And Poincaré, ever the skeptic, was still worried about impredicative definitions sneaking in, even with separation. He used this analogy of an enclosing wall built by the axioms, warning that paradoxes could still slip in if the wall wasn't perfectly defined.
So others tried to come up with better definitions for definite property.
Yep. Weil and Skolem suggested using first-order logic. Basically, a definite property would be any property you could express using the language of first-order logic, with its symbols and rules. It was a way to make things more concrete, more formal. Frankel, on the other hand, tried to axiomatize the notion of definite property itself, coming up with a set of rules for generating properties.
But Zermelo wasn't a fan of these approaches, right?
He had a couple of issues. First, he thought using first-order logic kind of smuggled in the notion of finiteness, which he thought should be derived from set theory, not assumed from the outset. Second, he knew about Skolem's work showing that first-order systems with infinite models always have countable models too. And he thought that was a problem, because set theory was supposed to be all about uncountable infinities. He felt like first-order logic was too limiting. He actually ended up using a second-order notion in his later axiomatization, just to be safe.
Okay, so separation was a bit of a work in progress. What about the other issue, the completeness problem? What was that all about?
There were two main aspects to this. First, Zermelo's original system couldn't handle a lot of basic math. Like, you couldn't really define the rational numbers, the real numbers, or even things like ordered pairs, which you need to define relations and functions. He tried to define set equality by size for disjoint sets, but it wasn't a very general solution. And defining the cardinality of a set as the set of all equipotent sets, as Russell tried, led to weird problems, like saying a singleton set has the same cardinality as the universe of all sets. Yikes.
So even though Zermelo wanted to build a foundation for numbers, functions, and order, his initial system didn't quite get there.
Yeah, it was a good start, but it needed more work. And the second aspect of the completeness problem was that it didn't fully capture Cantor's theory of transfinite numbers, the ordinals.
So where did the ordinals fit in?
Zermelo's second proof of the well-ordering theorem did use the idea of subset orderings, which hinted at a way to deal with ordinals. But his system didn't have a clear way to define ordinals themselves as sets. It was missing that piece.
And this is where Kuratowski stepped in, right?
Mm-hmm.
He was the one who figured out how to represent ordered pairs and orderings using sets.
Kuratowski was a key player. He took Zermelo's ideas about subset orderings and ran with them. He developed a whole system for representing linear orderings using sets, and he even argued that this was the best way to do it, that set theory should be able to handle these concepts internally without needing to introduce ordinals as separate primitive objects. He wanted to keep things elegant and self-contained.
And he even managed to avoid using ordinals in some pretty complex definitions that traditionally relied on them.
Yeah, he showed that you could derive a lot of important theorems directly from Zermelo's axioms without explicitly invoking ordinals. He was like, look, we can do all this cool stuff without those fancy ordinals.
And his definition of the ordered pair, AB as AB, was genius. Right?
Totally. It was a simple but profound insight. It showed that you could define something as fundamental as an ordered pair using just basic set theory. And once you have ordered pairs, you can define Cartesian products, relations, functions. It was a huge boost for the expressive power of set theory.
But there were still some cardinality issues, right? Like being able to create sets with certain larger infinite sizes.
Yep. Frankel and Skolem noticed that Zermelo's system, even with Kuratowski's improvements, couldn't guarantee the existence of sets with cardinalities like A omega.
Aleph omega. Just a reminder for our listeners, what's that all about?
Aleph omega is the next level of infinity after all the Aleph null, Aleph 1, Aleph 2, and so on. It's like the first uncountable infinity that's bigger than all the countable ones. And Zermelo's axioms couldn't quite get there.
So how did they fix that?
They introduced a new axiom, the axiom of replacement. It basically says that if you have a set and a rule that assigns a unique set to each element of your set, then the collection of all those assigned sets is also a set. It's like a superpowered version of separation.
And the exact way you define that rule was important, right?
Absolutely. Frankel's initial formulation wasn't quite right, and it led to some weird consequences. Weil and Skolem came up with a better version using first-order logic, and that's the version that's usually used in modern set theory.
And Zermelo was initially hesitant about this new axiom, but eventually came around.
Yeah, he wasn't a fan at first, but he eventually saw the light. He included a version of replacement in his 1930 axiomatization. It was clear that it was needed to build a truly comprehensive set theory.
Okay, last piece of the puzzle, ordinals.
Yeah.
How did those finally get integrated into the axiomatic framework?
This is where von Neumann comes in, and he did it in a really elegant way. He said, hey, let's just define ordinals as sets themselves. And his definition is beautiful. Every ordinal is the set of the ordinals that precede it. So 0 is the empty set, 1 is the set containing 0, 2 is the set containing 0 and 1, and so on. The successor of an ordinal is just that ordinal plus itself as a new element. And the order of the ordinals is just set membership. It's all very neat and self-contained.
So von Neumann basically found a way to represent ordinals using the very building blocks of set theory itself.
Exactly. And his definition perfectly captures the essence of ordinals. It's all about sets built from the empty set with the order given by set membership.
And there's a clear connection back to Kuratowski's work with subset orderings, right? The idea of using inclusion to represent order keeps popping up.
Yeah, there's a definite echo there. Both Kuratowski and von Neumann were tapping into the same underlying idea, the idea of using sets and set membership to represent order in a rigorous way.
It's interesting.